Hello, in this video I want to take a look at how to solve separable equations. That is, if we have a differential equation like this one over here, how do we find the solution? What function y derivative gives that? Before we get into that, I want to talk a little bit about something, a little bit of ideas behind this technique of separable equations. Now we know in math, basically any time I do something in an equation, I have to do it to both sides. It's this idea of the balance of an equation. If I'm solving for x here, I can't just divide by 2 over there. I have to divide on both sides until I get x equals 8. Whenever we do an operation on the equation, we have to do it to both sides to make sure things stay in balance. So there was dividing as an operation, but here I want to challenge you to think of differentiation or integration also as an operation on functions. Okay, in this case, I have f of x equals x squared, and I say, take the derivative. Well, you're not just taking the derivative of x squared, you're taking the derivative of both sides like this, d dx of both sides. On the left, we just kind of have notation for it. F prime of x equals 2x. There's the actual derivative. But we did it to both sides. Same applies for integration here. Okay, I have f of x equals x squared, and I say, take the integral. Well, in this case, our notation for integrating is integral symbol, dx, integral symbol, dx. So this integral sign along with the dx, the integral sign along with the dx, where this variable matches up with the variable I'm integrating, together they say, hey, integrate this. And once again, at least for this, we have notation. Capital F of x is equal to x cubed over 3 plus c. I integrated both sides. It's something I can do. It's an operation of sorts on a function. So I wanted to get across this idea that we can think of integration as a operation. It's an operation on a function. So long as we do it to both sides, we take the integral of both sides, we're okay. We kept it in balance. That idea is at the foundation of how we solve differentials by this process, separation of separable equations. Okay, so first example here, we have dy divided by dx equals 6 minus x squared divided by 2y cubed. What we want to do, because integration involves both kind of the integral sign and that dx, they kind of come as a pair. Together they mean take the integral. And of course there's theory behind that, the Riemann sum, and how that sigma sign means take the summation to infinity. So there's theory behind it, but we can just think if I have the integral sign and dx, I can do the anti-differentiation process. When I have a differential such as this, if I can separate it to get everything with y's on one side, everything with x's on the other side, I'm good to go to solve it. So looking at this equation, I'm going to first multiply by dx. So once again, we see the beauty of Leibniz notation in that we can kind of separate that dy over dx as a sort of fraction. And then I still have a y on the right side, so I'm going to multiply both sides by 2y cubed. What that does for me is on the left side, I only have y's, and on the right side, I only have x's. In fact, we have separated the x and the y's. That's why we call this a separable equation. We are able to separate the two. Now, take the integral of both sides. And notice, this is correct here. I have integral with dy, integral with dx. They come as a partner. On the right side, it's very familiar, the integral with respect to x. And on the left side, it's integral with respect to y, but good thing, my function is in terms of y. So I'm integrating with respect to the same variable, so it's going to behave just the same as with the x with respect to x. Okay, so what this looks like then is a couple power rules. So on the left side, I'm adding 1 to my exponent and then dividing by that number. On the right side, a couple power rules, 6x minus x cubed over 3. But remember, we're taking a indefinite integral, so I have plus c's. But here's what I want to say. We only need 1 plus c on the right, because technically on the left I can add plus c sub 1. On the right, I'll call it plus c sub 2. Well, those are just some constants. So to make it simpler, I could just combine them. So minus c sub 1, minus c sub 1 on both sides. And then this right here, I can just say, well, let's say c sub 2 minus c sub 1 is just equal to c. Okay, that's a little thing we can think about to make life easier and rewrite our equation as this with just 1c. That's why when you do separable equations, you will typically see just 1 plus c, and you're like, well, I got to do it to both sides. Well, we are, but we're just going to write it as that because it's just a constant. And then, if possible, we're going to go through this and solve for y so we can get an explicit function. So first of all, this reduces to 1/2. So I need to multiply both sides by 2. So I have y to the 4th equals 12x minus x cubed, 2x cubed over 3 plus 2c. Once again, with this, we'll see something we'll do with our constant there. All right, and now to get rid of y to the 4th, I've got to take the 4th root of both sides. Okay, and that will cancel out the left side. So I end up with the equation y is equal to the 4th root of 12x minus 2x cubed over 3 plus k. That last thing where I said k, that's unnecessary. Basically what I'm doing is saying 2c equals k and leaving it like that. You could just keep it as 2c. It's up to you, but it depends on your preference there with that. There's my differentiable equation, the answer to it. So basically what I'm saying then is the derivative of y equals the 4th root of 12x, so on, is equal to this. So I found the function that makes this statement up on top true. And I did that by separable equations. Okay, we're going to try this again. We're going to try and solve this differentiable equation. Here we have the derivative and we also have the function itself, so it's a differential. I would encourage you, when you are looking to see if this is a separable equation, write your y prime in Leibniz notation of dy over dx, because it's that fraction there, that ratio that we are looking to separate. If it is a separable equation, we should be able to get all y's on one side, all x's on the other. I like to keep the y's on the left side, as that is traditionally how we see it. So in this case, we're going to add that second chunk over to the right side. So we have this equals x times 1 plus y squared. I'm going to have to get that 1 plus y squared back over to the left. But first, I want to deal with this divided by dx portion. So I'm going to multiply by dx, and we have y times 1 plus x squared times dy equals x times 1 plus y squared times dx after I multiply both sides. And now I'll do 2 steps in one. First, I'll divide by 1 plus y squared on both sides, and then I'll divide by 1 plus x squared. That leaves me with y times dy divided by 1 plus y squared equals x times dx over 1 plus x squared. We basically have the same thing on both sides. Now, one thing to caution you here, because we are ready to take the integral both sides, but make sure your dx's are in the numerator, okay? A dy down in the denominator, it doesn't mean much. We need it in the numerator, okay? So both dy and dx need to be as that. Okay, so now we can take the integral of both sides, and we see we have integral dy, integral dx, so we have the notation there to do our antiderivative. I will do y in blue here because you kind of see we're going to have to do 2 u substitutions. So first, I'm going to let u equal 1 plus y squared. That gives me du equal to 2y dy. Okay, so we're going to divide by 2. And that gives me, we have the integral of 1 over u with a 1/2 out front du. And that equals, Going to green for the x's, we're going to let w equal 1 plus x squared. dw is then 2x dx, and we see the same thing. So that equals 1/2 integral of 1 over w dw. I have a 1/2 on both sides, so basically I can multiply both sides by 2, and we can just get rid of that 1/2. Makes things a little bit easier for us. I'll take the integral now of both sides. Integral of 1 over u is natural log of u, and integral of 1 over w is natural log of w. And we'll get our plus c in there. All right, plugging back in our values, natural log of u is 1 plus y squared, and then w is 1 plus x squared. Now, when you do these separable equations and find solutions, you don't always have to solve for y, because sometimes it's nearly impossible to or very hard to, so you don't always have to. This one we can make an effort to in fact solve for it, so we are going to try that. So I need to break that y out of the natural log, so I'm going to take the I'm going to exponentiate both sides, leaving me with 1 plus y squared equals, and nicely it cancels out on the other side too, leaving me 1 plus x squared. Now do be careful, this e, what I basically have is exponential property where this goes to e to the natural log, and because it's addition up in the exponent, it's multiplication down low. So I have 1 plus x squared times e to the c is how that will simplify. I will subtract 1, so I have y squared equals 1 plus x squared times e to the c minus 1. To make life a little easier, I'm just going to say e to the c is equal to k, okay, because e to the c is some constant. And then we'll take the square root of both sides. So we have 1 plus x squared times k minus 1. All right, that is the general solution for our differential. But you might have noticed this has a particular solution it's asking us to find. It says, find the solution of this differential such that y of 0 is equal to the square root of 3. That is, when I have this, when I plug in x equal to 0, it needs to equal square root of 3. This is where we're going to have to solve for that k to find the particular solution. All right, so I have y equals the square root of 1, because I'm plugging in x equals 0, times k minus 1. Oh, but when x is 0, this equals square root of 3. Okay, so essentially I am left with this equation here. Let's try and get to k, so we're going to square both sides, add 1, k equals 4. That was actually easier than we might have thought. Therefore, my particular solution is y is equal to the square root of 1 plus x squared times 4 minus 1. All right, and there is our particular solution.